Welcome back to Old School Coding, where I am in the process of building a old school simulation of an old school microcomputer using old school techniques. That is, I'm writing code in C99. I am using Make to do my builds. I am using Emacs to do my editing. And the eagle-eyed among you will have noticed a small change from previous episodes. You notice my editor has a slightly different font. This is actually the console font from the old Sun workstations, which were my first actual serious career, serious portion of my career doing software engineering. So I have fond memories of staring at this font for hours and hours and hours, and I think it is not as good a font as some of the modern ones, but I'm going to use it for a session or two, and we'll see if it grows on me again. We do see. I do need to check that I have proper support included for the Greek characters. I do indeed. So there's my microsecond and my delta tau. So as long as those are good, and let's add in phi sub 1 is the phase 1 clock. So phi's look not too bad, and the subscript 1 is in the right place, and the superscripts are in the right place. Okay. So this font it doesn't look like I'm getting anti-aliasing on the font, so it's a little bit jaggy. You probably won't notice it unless you're watching this at high enough resolution, but if you aren't watching it at high enough resolution, you may not be able to read it. So, what are we doing today? I've got the 8224, which generates the clocks, and I've got the 8228, which captures the status information and provides the control bus. We have implied a address bus and a data bus coming from the 8080. Now, the 8080 chip itself is large and complicated, and I think that in order to at least make it a little less daunting when we start swinging into it, I'm going to build a few more things that go outside. So when I start working on the 8080, I'm going to want to throw sequences of assembly code at it, and I'm going to want to watch it, step through them, and execute them. And the easiest way to do that, rather than writing half a dozen lines of code for each instruction I want to throw at the test, is to have a memory, have a ROM and a RAM, so I can put the data into the ROM, and I can start the CPU running, and I can run it for a certain number of instructions and have them print out what they're doing and check that. So we need RAMs, we need ROMs. I'd like an I/O device so I can, we need a serial console, and we need a paper tape punch and reader, because that's the primary paradigm in CPM for the serial. So we're going to pretend we've got a ASR33 teletype hooked up to this thing, bega, and a nice paper tape punch reader, which we will have separate from that. Yes, I know the ASR33 had a paper tape punch reader built in if you got a good one, but we're going to have a separate paper tape punch reader. I may fiddle around with the timing and pretend it's a nice high-speed one, or I may leash it back and say, okay, your teletype runs at 10 characters per second, and your paper tape will run that at some higher rate. I'll have to look up how fast that runs. I may or may not set up a device which will be a fancy virtual floppy disk drive. Floppy disks typically ran 300 to 360 RPMs. I think the fastest one was somewhere north of 1500 RPMs. So it's really very slow compared to modern equipment. But again, this was a piece of mylar sandwiched in plastic and fur. So anyway, before we can do that, I need an address space decoder, because if I've got all these things out there, I don't want every one of them listening to the dBn and WR signals. So I'm going to do a decoder. I-8080, actually, this is going to be a decoder, so I'll call it decoder.h, decoder.c. Okay. Decoder is going to have a lot of our standard boilerplate, so let's just grab the i8228.h file, file off the names. So decoder, address space decoder for 8080 like micro computer system. I'm saying like because it's quite likely that the way I set this up will require either no changes or minor changes that go from 8080 to 8085 to Z80. It may even work if we branch out and do a 6502 or 6809 or 1802. All of these are appropriate historically. We just need to figure out what kinds of things we want to do here. So this is P decoder, and so I need to.
He may need to be moved down.
Decoder like that. So we don't know what it's going to be in it yet, but let's check the rest of this. We have invariants to check. We need to initialize. It's probably going to be stateless, but it does need a name. It will be something I'm going to do is we're going to end up with imported signals for some very small fractions of the address space. I haven't decided what my granularity is going to be. For instance, if I had a granularity of 256 bytes and I had a memory out there that was 16 kilobytes, it would have to put its signal in a lot of slots. On the other hand, if I had a granularity of 8K, then I could never set up a 1K RAM chip. So we'll figure that out. Anyway, decoder linked, we'll have to take into account the fact that we may have a large array of pointers, signals, which may come and go. So, for instance, at boot up, we may have the start of the address space pointing at the ROM. And shortly after boot up, it may change over to RAM. I just realized that switching a shadow ROM in and out and possibly in the future doing bank select of a section of the RAM might be something that would necessarily go in the decoder. So that's an idea. A ROM wouldn't know it's being shouted in or not. That's external circuitry. So the decoder is taking the place of a whole bunch of discrete circuitry, discrete chips, discrete logic in a system where you might have a 3 to 8 decoder somewhere, and it might feed into enable signals for more 3 to 8 decoders, and you get yourself 6 bits of decoding or 5 bits of decoding off the top of the address space. Anyway, post and bist and bench, these are all just stock, so this is really not a whole lot we need to do. So now I can grab this whole thing, take it over to the implementation, take away extern, and change close paren semicolon to close paren, open paren, close paren. I need to give parameters names. Oops, missed one. So decoder is called dec, and this should be good enough. To keep the compiler warnings from happening, I'm going to go ahead and put my void dec to do implement this. Okay. Now we haven't done a build yet because we haven't touched any of the files that were already being used in the build. I'm going to change that now. Main.c. The decoder will be included after 8228. So, starting from the top, start to find a keyboard macro, search for 8228, go to the beginning of the line, duplicate the line, find that again, erase it, and put in decode, or decoder. and that duplicates all those lines out. Now, these exist, again, if I didn't mention it before, these long lists of post functions and BIST functions and so on, they exist because the C language does not make provision for having something in a file with an initializer that triggers code to run at runtime before main starts or while main starts. So we have no way of having a C file land in a project and register itself and just be part of the system. We have to go somewhere else and say, hey, you. And the way I've chosen to do that is to have Boast, BIST, and Bench actually call in like this. Now, I could have set up something where there's a first thing I do in main, which is call in the dynamic library load stuff. No, I'm not building these as dynamic libraries, but I could have something that says package init, and we could do a package init on every package, and it would add itself to a list of posts and list of BISTs and list of benches and so on, and then we could have a mechanism out there. I think that that's a lot of support code to add to do that. It's not something that's built in. It's something that would be built into a decent package manager. C is famous for not having a decent package manager. We're not going to change that here. So we've got that. Save everything.
Would be faster than redoing it.
And what I'm seeing is that the make file is saying it doesn't know how to make decoder.o and main.o for some reason. So we're going to go back out here. It's probably because C-star is not defined. Support.h, and that is somewhat better. And I have something called S8228, which is bad. So this is S decoder. Okay, this module expects to see the control signals produced, signals from the 8228, indicating what kind of cycle is present, and may also need, and will also need, may also need see some signals from the 8080 itself. So I am waffling a bit here because we're declaring a memory read or a memory write on the instant where we get the status bytes. Okay, so when the sync comes down and we get the status strobe, we're going to see this as a read or a fetch. Not the right, but if it's a read or a fetch from memory for either instructions or data, we're pulling the memr right then, or we're pulling the IOR right then if it's a device access. I think the address is valid. The CPU is still outputting the status byte, and we aren't supposed to start pushing our status onto the bus until dbin goes active. Now, perhaps my strategy will be to put my data on the bus when dbin goes inactive, but then that begs the question, what happens first? The device reacting to the descending edge of dbin, or the CPU deciding to snapshot the data when it releases dbin? So I may need to have dbin come into the decoder so the decoder can pass along to the chip. Okay, here's a strobe saying your address is valid. Here's another strobe saying please present your data. Here's another strobe says please accept data from us. It's also possible that we don't need that initial, the address is valid. In a real hardware system, that's where the chip would turn around and say, oh, please go into a wait state. So we would address a ROM, and the ROM would say, please give me 2 wait states because I am slow. And it would do that well before dbin went active. For writes, I think the chip is just expected to accept it. I'll check the timing of the wait states on that. But yes, this means that any slow chips that might want to inject a wait state, they will need to have access to it. The decoder doesn't need to be part of that logic, though, so we're not going to worry about it. But we have identified that we have some signals that are going to be required here. Anyway, let's take a look at our errors so far. Decoder init takes a name and isn't using it. Well, that's because I didn't even start on this. So, decoder invar, the normal thing, we're going to, let's do init first because invar won't be called until after init. We're going to assert dec. We're going to assert name and name sub 0. So if somebody calls decoder init and they give us a null pointer for each one, or the name is empty, we're going to just, no, never mind. We update the name. Currently, we don't have anything else in the structure. And decoder invar, we could do that. And again, I'm going to often follow this convention of sample the fields into local variables and deal with them. Even though the compiler is perfectly capable of optimizing, if I make an external function call that's not visible during compilation of the source unit, okay? In fact, I think that's any call to somebody outside that unit of source. The compiler cannot assume that the contents of dec name are unchanged. So by doing this, I'm telling the compiler, sample it, and we just can use it from here. It's also not clear that it's a win, because if we do that external call, name has to be stored in our stack frame somewhere. So now accessing name becomes get the address of the stack frame, go find name. And the other one is go find dec, go find name. So that may or may not be a win these days. Back in the day, this might have been a win. So yeah, I'm doing that just for my own personal sanity. Okay, so that assures that we have a name for the decoder. Decoder linked, I'm going to say decoder invar of dec. For now, I think the process of linking up the decoder, I may be able to do the invar, I may not. Let's take a look at what we need. I'm going to pop up my, I don't have that too handy right now, so let's go grab my document on the 8080 so I can look at the timing on all of this junk. 8080 Microcomputer Systems Manual. Plop that over onto the right desktop. Oh, that's the wrong viewer. Let me do this with the proper. Yeah, XPDF. Okay. Now, I'm not sure this is going to bring up the right thing, and it doesn't. There we are. Nope. You know, it helps if I fix the right window. There, that one. And this guy, let me make sure I have the correct window selected in OBS, and then tell it to look at the right thing. What the heck is going on? Okay, you're going to be stubborn. We're going to remove you from OBS and try again. Window capture. There we go. So there's the manual that I've been working from. If I wanted to fiddle around even more in OBS, I would basically chop off all of the tool around it, but we're in a hurry here. I'm interested in looking at the timing of the read and write on the 8080. Actually, let's take a look at the 8080 sheet. Instead of the block diagrams we've been working from, I'm going to scroll down here till we get to the actual 8080A. There we go. And we see here that the address goes valid way out here. So sync goes valid well before the address. So when sync goes valid, the address is not yet valid. Okay. Let's check that TDA. So we have up to 200 nanoseconds from Phi 2 to light up that one. But TDC says we only have 120 nanoseconds to get to the control signals. So as sync rises, which is when we are going to be letting up those control signals, we don't even have an address. All we know is it's going to be a read. You know what I'm going to do? I'm going to violate timing on the 8228 because there is nothing useful we can do knowing it's a memory read until we have enough address bits to start decoding the address. So when does DBN occur? DBN occurs sometime later, but we know the address is valid before DBN starts. So the edges we have are sync edges and DBN edges and status strobe edges. Okay, status strobe occurs sometime during sync. Oh, wait a minute. Status strobe is occurring right here at the end of the cycle, so we actually sample it here. We might be good. What's TDA again? TDA says 200 nanoseconds from this clock. This guy is 5 clock cycles long at 55 nanoseconds each. So yes, okay. So address bus is valid before we hit the status strobe. Yay! But we still need to get DBN going. Next question is, what do the memory units do knowing that they have an address coming in, but they are not being told they have data? A real piece of hardware would start the process of decoding internally and finding the memory cell and getting the value of the memory cell gated back out onto the lines and into buffers so that when time comes to produce the data, it can do that. And software simulation, of course, it all happens at once. So I think, I'm circling back around to this, I think I want to delay onset of MEMR and IOR and int_a until DBN goes high. So let me cancel out the PDF display here. We're going to do that. Timing is similar. Well, we're going to have a major deviation. Timing. The 8228 asserts MEMR, IOR int_a very shortly after STSTB. But at that time, however, in the simulation, our memory devices, our devices have little they can do with the address until it is time to return the data. Okay. Tossing my PDF back up on the screen, we're going to do a little more thinking because the cat wants to talk too. Here you go. So the second consideration I have to do for the timing on this is, what about ready? So under what conditions would a chip, would I want a simulation of a chip to assert ready? And is it okay if I don't assert it until dbn goes active? Well, dbn goes active. This says that ready needs to be stable for a certain amount of time before this falling edge. Is that all you wanted? That's all she wanted. Just wanted to come say hi. Let's see here. Okay, for this I need to go back to the other timing diagram, which is more interesting, more easily consumed. Ready is sampled here. So dBn goes high casually sometime here. Ready goes low at some point. Now, nominally, somebody's driving ready low during phi 1 on this diagram. On this diagram, phi 1 being high is the proxy for the status strobe. So status strobe goes out, somebody's jamming ready to low immediately, which is not a bad idea. You make ready low, and then when somebody is ready, they make it high. So sometime here in the latter half of phi 2, at some point, somebody's looking at ready, and if ready is low at some time here leading up to this descending edge, we're going to insert a wait state. And then during the wait state, we check again during that same part of the cycle. And when it's high, we can then continue onward. So the question is dBn already set? And dBn is already set. So it is valid for chips to pull the ready line low when dBn goes high. And the way I'll make that work is that dBn will go high, probably coincident with the phi 2 edge. Let's take a look. Can we do that? So timing of dBn. dBn is TDF after the rising edge of phi 2. So 25 to 140. So nominally, this would be one oscillator clock after the rising edge of phi 2, unless we had a really, really, really slow clock. So it is entirely valid for me to quantize that dBn rises when phi 2 rises. Because, again, the CPU only gets phi 1 and phi 2. The CPU is not getting the primary oscillator. It's not hooked up to the CPU. And I am not doing a delay thing. So the timing it's going to come out of the 8080 is that the sync is going to go high, TDC, which is up to 120 SSO. So phi 2 will go high and sync will go high during T1. During T2, sync is going to go low and dBn is going to go high. And that's going to say, okay, all you memory chips out there, you've had your address, you've done some things, we're going to go high. And then we have this long from here to here to pull wait. Well, to not assert ready. We see here the timing on ready relative to the falling edge. It's TRS before the falling edge. TRS is on the next page. Yeah, we have 2 pages here. Let me see if I can widen this out. And move it onto the screen. So we're going to take a look at this timing really quick. I need to be looking at the 8080 timing. And I need to do the other kind, so change that. There we go. So here's our timing diagram. Yay, I got 2 pages up. So the ready signal needs to be set up. TRS is the setup time, so at least 90 nanoseconds before the falling edge is where the real hardware 8080 expects ready to be stable. So for 90 nanoseconds before this falling edge, you're either ready or you're not. And after the falling edge, we're supposed to hold it for T H. So we have to hold it until 0 nanoseconds after. So we've got a little bit of time before Phi 2 falls to have ready stable and hold it stable. So that tells me that the 8080 simulation will be looking at ready at that point. So next question is, when is ready my latched? I think I latched ready in the clock stuff. Reset, and what did I latch in the clock stuff? Let me move that out of the way. A224. Yes, these latch, reset, and ready. So I need to have my reset. What I'll be actually modifying is RDY in, and I need to do it before the 8224 latches it. It synchronizes reset and ready to a specific phase of the clock. So reset and ready are latched here. So Phi 2 begins in cycle 3, phase 3 of the clock, and then after that, so 55 nanoseconds after the rising edge is where we will latch it. So this means that doing this, my memory chips need to have their ready on the bus within a very, very short time of DB in going active. So that's why your hardware is going to look early and get the address decoded and get it ready to go. And why my simulation is going to have to do it right on the edge with DB in.
Sure, whatever.
Okay,
I lose count.
back to the decoder. So what does this mean for the decoder? It means that the decoder will be listening to the signals from the 8228. I didn't change it, did I? I did not change the timing on the 8228. So what I'm going to do instead is the decoder will be listening to DB in for its timing, and it will be listening to all of the control signals. And it will need to have a whole bunch of outputs. Mem page. We're going to have one output per page of memory, so a decoder page of memory. I think I'm going to output a signal for each kilobyte because I remember working with 1K by 8 memories, and in fact there are 1K by 1 static RAMs that I was working with back in the day. And I'm going to do the same thing for ROMs, separate page size. In fact, I'm going to say I will only be dealing with 4K by 8 ROMs from now on. Do I want to do that? Yeah. Well, wait a minute. Let's look back at our document here. They do document the available RAMs and ROMs that Intel was selling for this system. So ROMs range from the 8702 up to the 8316A. So 8702 was 2 kilobits.
As long as the leaks aren't.
So it's 2K by,
They don't seem to be, so.
I believe that's by 1 bit. No, it's by 8 bits. So 256 by 8 bit. So we would need to have 256 control signals coming out for this. I think this is too small. I think what I'm going to do is say that my simulation target is going to be larger. So let's take a look. 8 kilobit is 1K by 8. So we're starting to, so 8708 may be the smallest one we want to do. So 1K ROM. I'll probably normally want to be using bigger ones, but let's allow for the possibility of a 1K ROM. 2 kilobit masked programmable read-only memory is, again, 8 by 256 by 8. 8K by 1 bit. Is that 8K by 1 bit? I keep thinking that I'm going to get by 1 bit stuff in here. This is all by 8 bit. So this is 1K by 8 bit static MOS ROM. So 8308s are nice. They're getting to be larger. So the 8308, you know, they got all the ordering information. So you actually tell Intel what you want in it, and it will do the right thing. 8316 is 2K by 8. I will probably mostly use a simulation of the 8316. In fact, it's just going to be a generic ROM, and I'm going to call it 8316 because I'm going to configure it similarly. But the differences are going to be subtle, but present. And my simulation will have to be 8316 plus some additional circuitry. So, get an idea of what I'm looking for here. We have 3 chip selects, and I believe that you tell Intel what you want these to be, either active high or active low. It's got 11 bits of address coming in, so that would mean that I would want to fully decode 5 bits of the address space, so down to 2K, and output stuff. What's our timing look like? Here is the timing waveform here, and this says address to output delay time, so TA, from the address going valid to our output going valid, typically is 400 nanoseconds. Okay, our entire T-state is 450 at 20 megahertz and 450 to 500 nanoseconds. So, yeah, typical. But maximum could be up to 850 nanoseconds between getting the valid address to getting this valid. That's because this guy's always watching the address bus. So the 8316 doesn't care whether it's enabled or not. It's always on the fly, decoding the address bus and keeping track of that. And it might take it up to 850 nanoseconds to cascade all of the decode information through and get the things going. So from the last change in address, that could be that long. Now the chip selects, programmable chip selects, we got TCO. So from TCO, we've got 300 nanoseconds that we can take. So TCO to 300 nanoseconds here. So you're not going to get valid output until both of those conditions have passed. Okay, so this is what this tells me is that this ROM is kind of slow. We may need a wait state. And when the chip selects change, we have TDF, which is from 0 to 300 nanoseconds. We may hold on to the output. We may not get high impedance for another 300 nanoseconds after that. So designing the hardware around this means you're probably throwing in T-states, wait states around the ROM. And that's actually real. Executing out of ROM was always slower than executing out of RAM. So there's our ROM. Our ROMs may want wait states, but we know that we can manipulate RAID as dBin goes high. ROMs don't care about WR. So the 8316 is going to be our golden boy, but we're going to set up the rest of it so we could go to 1K instead of 2K. I am not going to support the decode down to the 256 byte size. Yeah, that's just a little excess. RAMs. So 8101, the simplest, cheapest one was 1K bit, which is 256 by 4. You'd use several of these. So 8102s. Notice this is only a single bit. So this is a array, which is 1 kilobit of memory. So 1K by 1 bit. You'd have 8 of these side by side. And, oh goodness, these guys are slow. Let's look at the more, as we go through this sheet, they get bigger and more expensive and faster. So 8102, 400 nanosecond access time max. We're getting up to where we don't need wait states.
Another Drake token.
Having memory with no wait states was always a great thing.
Need the Drake. Otherwise, I'm leaving it on the body.
And the 8107 is 4 kilobits. We're starting to get decent. It was still 1 bit wide. Okay, so this is a 4K by 1 bit. You'd put 8 of these guys in, you'd have 4 kilobytes of memory. Okay, now we get out here, static RAMs. Ultra low standby current was the special thing here, and then beyond that. So our high-end RAM that we would want to look at is this 8107. And we're looking at this again. Now, again, it says if there's a certain amount of time after address stable where we can get the data. So here is our chip enable has to go high here. TAC is come on. I got away from the chip I wanted to look at. Here we are. So addresses in CS are that top line. Okay. Address stable, we get chip select is part of address. That makes sense. CE is T underscore AC, which is, I believe, on the next page. Yeah, let's change the even odd page thing again. Yeah, it didn't do what I wanted it to do. That's okay. Anyway, so we've got, this just says that the chip enable has to be after this, 0 more nanoseconds. We've got a rise time. Write enable must be high because this is a read cycle. And because it's a read cycle for some period of time, at this point we're going to drive our data onto the bus. And what the heck? Does it drive all the data to 0 during this time? I'm not sure what the hardware does here, but this tells me that at some very, very distant time from when we got the chip enable, we eventually get our data back. And it's up to the system around us to work out how to wait for long enough. So T-access is here and TCO is here. So let's look at T-access and TCO. T-access is 130 nanoseconds or longer, and TCO is the output delay, which is up to 250 nanoseconds. So this distance from here to here can be up to 250 nanoseconds. Well, that is only half of a T-state. So these guys can very neatly work inside our T-states without any wait states, which is why you want static RAMs. In fact, if your static RAM required T-states, they probably would have done more in slower cycles in the CPU. That's the thing, is you design around the entire system. For the write cycles, address stable, chip enable. Now, WE can go all over the place, but at some point it has to be low with the data in stable. So we're data changes, our write enable changes, and this sounds to me like we may be messing about with the contents of the RAM, but eventually it goes low and our data is stable, and that kind of sets the final value. And write enable gets released at some point, and then we're done. And our times, this is TCW, is from rising edge of chip enable to end of write enable, and TCW is 150 nanoseconds or more. So this says that we need at least 150 nanoseconds from chip enable to the rising edge of write enable to assure that we're all completely stable and do the right thing. Great. So now we can tuck all that knowledge in the back of our heads and forget it, because we don't need any more of that for the decoder. PDF viewer off. And off screen, I am going to put us back on the single page view. And make it smaller again so it's not taking up too much space on my second screen. Oh, come on. There we go. Don't be fiddly on me. And move it mostly out of the way. So what did I learn from that? I learned from that we aren't really interested in the falling edges of memar and IOR and int A. What we're really interested in is watching for dbin and then making decisions at DBN based on those guys. So none of these chips needed to do anything. If they could do everything in 0 time at DBN rising, they didn't need to do anything any earlier. So we need P edge DBN. We need that from the CPU. Okay. Watch me change my mind again. So what we're saying is when we see the rising edge of DBN, we're going to look at all 3 of these and make a major decision based on them. Wouldn't it be nicer if we could just get memr and say, oh, this is memory request and DBN is going high? Yeah, I am going to change the 8228. So where we actually assert this, start reads, isn't going to actually start the reads, okay? Or actually, it will, but we're going to start the reads when the DBN rises. So just like write going low starts the writes, DBN going high is going to start the reads. Latch status no longer starts the reads, it just latches the status. So, with the timing of DBN, is there any chance that DBN will interact with anything else? I eventually said I wasn't going to even muck with bus enables, so we're not worried about that. Later, when we come back to deal with bus enables, we'll say, okay, when does bus enable happen relative to DBN moving? So that should change that. And at this point, we may in fact, oops, I stopped my build loop. That change probably caused us to start failing. No, I don't want to change the group of README. The perils of having a caps lock key. Ah, there we go. That makes sense. Let's not do these quite yet. I want to be able to see the 8228 not failing its tests. And indeed, it is going to fail its tests because we have changed the timing of these signals. So, make a change, make it work, fix the tests. So, yeah, all these check case reads, the timing changes in. Fortunately, they're all in one tester, so we're going to say impress the data, status strobe there, and nobody goes yet.
Watch out for deep water, Tweety.
Edge high, no change status strobe. DBN, that's where our outputs are going to go. So, so check outputs, we are failing a test that memr is 0.
Oh no, Tweety.
Oh, right, I didn't change it here. We've got 2 cases for the reads. We've got the case where hold is being used and the case where it is not. We just needed to change it here. We're delaying our update of those outputs by not changing them on the status strobe line, timing edges. And that did it. Okay, so we have changed the timing. We have changed the test to test the new timing. And no other modules depend on it yet. We're now working on the first module that does. And it's now set up to do the thing that we want to do. Let's put the header file on the left again because that's how I'm used to looking at this. Our input signals are going to be output signals from the 8228. So these 5, those signals will go active at the beginning of the access. So the address will be valid, and for the reads, we're ready for the read, and for the writes, we've presented the data for the write.
Leather bracers.
These are all P edges. So what do we want to do here? Inside linked, we're going to say that these guys are set.
And 3, 2, 1.
It means that we don't get to do the invar here because we are going to start asserting.
Hunter book and another warlock book. Hunter book going to
Edge,
supervisor.
invar, that. So what else do I need to do? What do I generate here? My outputs are going to be owned by their destination.
Shaman, mage, and druid.
So we now have P edge.
Going to boom.
I'm going to say mem rd. So I'm going to have memory read signals. So if I see a read in a page, I'm going to gate that. I'm going to send memr on to whoever that is, and mem wr like that, and then essentially this is one per each of these. Now int acknowledge comes through. We don't really have a decode for interrupt acknowledge because the CPU doesn't say this is interrupt number 5. Decode of interrupt acknowledge is something that a interrupt controller would know because the interrupt controller is receiving 27 different interrupt lines and it sends one onto the CPU. And when it gets the int act cycle, it then does the right thing. So we actually are not listening to the int A. Okay. Now these guys, I think I ended up saying RAM and ROM of 1 kilobyte each. Okay. How about I say 1U less than 1U shift left by 10. So we're going to have 10-bit addresses. Our address space is 16 bits of address space. Okay. Define decoder. So the RAM. All of these guys are going to be address space size, mem space size. So memory has an address space size of that. These arrays are the only place where we need to know this number. Probably I better actually express this by bit shifts. Dec mem as bits 16. And am I going to do RAM and ROM separately? Yes, I do. Yes, I am. So RAM page bit, RAM page. PO bits. So PO is page offset. So the page offset for RAM is going to be 10 bits, and for ROM is going to be 10 bits. Let's mess with this. Let's say, make sure the code works for these being different. Okay. So the incoming value here, our size is 1 left shifted by 1U left shifted by the difference. Now, is that something I'm going to want? Yes. So devices. Devices are unique ports, so and there's only 256 of them. During init, I need to zero out these guys. Yep. And there's an easy way to do this. There's something called memset. Dec arrow mem underscore rd is the array. I want to put in the 0 value into every byte of that array. This presumes, of course, that 0 is the, 0 filling something gives me a null pointer. Am I willing to make that bet? I am not willing to make that bet, even though every CPU that we work with now does it. There have been times in the past when we've had processors where 0 was a perfectly valid pointer, and maybe the null pointer was something that the compiler recognized when you assigned it. Or maybe it didn't work at all. In the case of Vaxes and Unis, and I seem to remember that was a problem. I could be wrong there, don't hold me to that. Anyway, this will probably be a little better, so we're going to say, well, first off, I'm going to establish pointers in my code for these guys. So we want it to look like that. And these actually want to be a pointer to an edge, not a pointer to a p-edge. No, don't mess this up. These are arrays of pointers to edges, so they decay to a pointer to edge. There we go. And that would have been a compile error, which we didn't see, but we do have an unknown type because include edge.h here. Okay. Start keyboard macro, search for semicolon, kill to end of line. Go back to the space, kill equals dec arrow yank. Okay. Page, well, this needs to be unsigned. We're going to say mem underscore rd of page equals 0. And we're going to do the same thing for WR. Mem and ROM? No, RAM and ROM. Now, the reason why I have separate decodes for these, first of all, different sizes. Second of all, you might have a portion of the address space that has both RAM and ROM mapped in. And if this happens, what I'm going to do is what? What I'm going to do is slow. Okay, I give up. We're going to change RAM to mem everywhere. Oops. Not everywhere,
Going to Luga Luga.
because we don't want to have programs.
One.
And when we say ROM, those go away. So we have one thing called memory and one thing called devices. Okay, we are not separating RAM and ROM.
Also have a
So shadow is going to be a completely separate thing.
cracked view.
We don't have ROM reader write. We don't need to do this twice.
Priest, mage, warlock, druid,
Mem.
weapon token.
Now there is a valid thing where one address might be RAM or ROM. That's a case where if you're reading, it goes to the ROM, and if you're writing, it goes to the RAM. Now this is used in systems where you shadow the RAM and the ROM. And in some of those systems, I saw at least one design, I don't know if it was built or not, where when you read from the ROM, it automatically wrote it to the RAM all at once. So all you had to do was write a little loop at the beginning of the ROM that read the entire ROM, and that would shadow it into the RAM. And then you would do something to turn off the shadowing, and suddenly you're running out of RAM instead of out of ROM. Neat, huh? And it's faster because instead of doing a read of the data into the CPU and a write back out and having to have separate read and write pointers, which is, you know, inside the 8080 now you're doing, you're exchanging DE and HL. So you're saying read through M, increment HL, write through D, exchange them, write through M, increment. Okay. Instead of that, now you just have something that says read it. Okay. And if you're really clever, you can set up your system so that when you boot, it's not only shadowing, but it is reading from the ROM, writing to the RAM, and delivering a no-op to the CPU. So your CPU starts out, coming out of reset, starts at 0, goes zoop at basically 4 T states per byte of ROM, or 5 if your ROM's got a wait state. You're now copying it into RAM. And when you get to the end of that, you stop shadowing, and now you are at some higher address. You're at the end of the ROM, essentially, the end of the area you're copying. And you do something, like jump to 0 or whatever. So let's see, what is the current error is. We still are calling it RAM here. RAM is mem, prod mem. There we go, and page like that. So dev WR, these guys aren't set up yet, so this goes from mem pages to mem to dev. Okay. Now for I/O devices, the reading from a specific port number and writing to a specific port number, you're not writing to a port and then reading back the value you wrote. You are doing two separate operations. One is sending data to an I/O device. The other is receiving completely different data. So it is quite possible that when we have real devices, the device read edge is not going to be the same as the device write edge, not just by whether it's reading or writing, but may go to completely different devices. Quite viable. Usually they'll be related, though, because you get crazy if you just kind of assign a whole bunch of random ports to different things without, some sort of sanity. Anyway, so there we have our initialization, which sets these guys to 0. We have our linked. Okay, bear in mind that we are not going to demand that there's any particular guy out there decoding. But I think the next thing I'm going to do is I'm going to set up a ROM shadow. So there's going to be a notion of, are we shadowing the ROM? If we are shadowing the ROM, then what line are we pulling for the shadow? And when do we stop shadowing? And I think a shadow is basically going to say, if shadow is active, then all accesses go to the shadow. And that's basically saying if shadow is not null, it's active. Okay? So devices that set shadow need to know what they're doing, and they need to know to set it to 0. If shadow is set, then all memory operations are diverted to shadow. Memory read operations. Okay? So only read operations, but all read operations. So you can't, do we want to do that? Oh. Yeah, a real simple shadow system. We're just going to say all memory read operations are going to go to that chip. So we need to initialize shadow in init. Chips will either, somebody that needs to be shadowed in will place their edge pointer in shadow, and when they're done, they will null it out, which means I need to have a way of setting and clearing shadow. So set up or turn off the ROM shadow.
Yeah, finally.
So operation
Yeah,
is
that's
normal
what it
when the shadow is null, but if it is set to an edge to point to an edge, then all memory read operations will be sent to that edge rather than the mem_rd of p. So you'll be able to write to RAM, so you can implement a copy if you want.
Secret yourself?
Okay, but if you're reading, you're reading. So I think the normal thing would be that you shadow a ROM that lives in high memory down to 0, and you come out of reset, you start executing at 0, which is the beginning of the ROM, and the first thing the ROM does is jump to its normal address. And when you get there, at some point, the circuitry will either by noticing that it's now fetching from the ROM at its normal address, which is clever, or by responding to a device access. You have to do an output to a device port to do it, which is less clever, turn off the shadowing. I like the idea of automatically turning off the shadowing the first time you access the ROM at its normal address. If you do that, then you only need the shadowing on for a few cycles. In fact, you only need the shadowing on for literally 3 T-states. So you fetch the jump and the address and the address, and you go. Extern void decoder shadow decoder and edge. And we can pass a null in here, so I'm going to specifically say it's a p edge to kind of advertise to the reader that it might be null. So dev devs dev devs doesn't exist. It's dev devices. In fact, I'm just going to say deck devices here. Besides, I had dev at the beginning, so dev AS bits is, so the AS bits are going to be useful when we are doing our work, because we're going to have to shift the address down by the number of page offset bits and then do a masking operation by the difference between the two. And in the case of dev, we're going to mask it by that many bits. This allows us in a future version to say, well, what if our device addresses are 16 bits? I believe the Z80 does that. We'll get there. Maybe even the 8080. But as we see up here, we're back to working again. We're not doing anything yet, but we're working. we're successfully doing nothing. So, decoder power on self-test. What do I want to test so far with this? We have a decoder deck. I'm going to follow the strategy I used before and have a static void decoder test init, which is going to set up a decoder that we can do for testing. So this is going to be decoder init of deck. And we're going to do uppercase because we want it to set the name of deck to deck. Now, the uppercase macro says give us a default. We could put more defaults in that macro if we wanted, but give us a default one. Just give us a default. Okay. So deck, decoder invar deck, decoder linked deck, and in this case, we can actually check our invariants. I'd like to check our invariants at the top, but that would mean we would need to know that we weren't linked. So let's not check our invariants at the top. It doesn't gain us anything. Now, what invariant do we want to check for these guys, these pages? These are all set up by the time we get to invar. We're going to say if mem underscore rd of page, then edge invar of mem underscore rd of page. And we are. So if the pointer is set, then we want to check the invariant.
Crystals that are between the outer wall and the first set of pillars.
Similar here, mem becomes dev, and page becomes dev, like that. And when we reformat it, it's going to put in a whole bunch of new lines, except I've goofed and I didn't actually grab these guys. And you know, when I grab and copy, I need to make sure I leave the old one behind. So decoder test init is not called. So what we're going to do is put calls to that in all three of these locations. I think print top. It's time to actually do this. Make sure we're getting called. So the first thing that's happening is we're calling edge invar and it says assertion failed. Okay. So decoder invar does edge invars of all of these guys. You'll notice that in our testing, we didn't actually set those up.
Yeah, and be sure maybe
So before we create our decoder, we want to create edges. Now, by default, a edge that comes up will be 0, although you never know. There could be stuff in it, edge in it may or may not change the value. So let's find that parenthesis, and let's say edge underscore high of memr, because these edges want to start high. In fact, I am going to gather the edge inits together and then gather the edge highs together. We're just going to do it this way. So static init the edges, set them all to high, do the decoder init of deck,
there's one,
and then set the links for deck. say we're linked, call the invariant. Again, in the tests, we do not assume that the main functions will call the invariants out. And now we'll notice that we have everything running here. And the only difference in the outputs is we see decoder post running here. We see decoder bist running there. And then we see decoder bench running there. So we can now take out those prints.
Got one by stairs.
There we go.
Oh no, don't click the ones in the middle.
Okay. My wife is in a AQ raid in World of Warcraft, and apparently things are not going perfectly. That's all right. They never do.
Looks like it's gonna be all right.
Ba-da-boom. Where are we here? We're not actually doing any decoding yet, but we are passing the test so far. We're getting there. Okay. So we have 4 signals we're watching, and we have to have an address. P adder. And I'm going to say adder is my address bus. So inside invariant, we also need to say assert dec adder. And that's going to immediately fail because we're never setting it. So now inside link, well, before we link, we need to have it. So now I say static adder, so we have an address bus. Better. So we have an address bus which has our 16-bit address on it, or our n-bit address where n is decmem as bits. And we will not guarantee that the C data type is exactly the right size because we may have an address space of 18 bits or 36 bits or 20 bits. But we have an address bus, and we'll use bit shift and bit mask operations to extract fields from it. So we have asserted that it exists. And now we need to actually do something. So for each one of these 4 signals, we are going to grab the address. We are going to extract the page number or the device number, and we are going to grab the edge from the array, and we're going to yank on that edge. And that has to happen on rising and falling edges of this guy.
What we're trying to do is
So
get the crystals localized so we don't have to drag the ball so far. And there's really about 4 around the stone that we try to use. So
how do I want to do this? Inside linked, we're going to say, well, let's see. So edge on rise and edge on fall. So edge on rise of, well, let's get the local variables here. Oh, and I didn't update my signal names. Ooh, almost forgot that. Oh, I've got no signal names to update. So for each one of these edges, we want to do a rise and a fall. And I need to pass them dec, and they need to be a separate function, or R and W, I could pass the memread and memwrite themselves. And IOR and IW, so the only difference is going to be how many bits we extract, so we're going to have 2 service functions. Static void dec underscore mem is going to take a p edge star. Actually, it's actually going to take what? Yeah, p edge star. Now, I know this is actually going to be a pointer to an array of a specific number of pointers to edges. So this will look like the following. Edge on rise of mem_r is going to be calling dec mem, and it will be passing along mem_rd. And then we're going to do the same thing with edge on fall. Okay,
Absolutely.
so
Just
what it will
open
have to do is copy it in. Oh, I don't get the pointer to the edge, so I don't know whether to rise it or fall it. So this needs to be mem rise and mem fall. And I am thinking that passing along the mem read is just going to be too much sugar for a nickel. So what I'm going to do is, mem read rise. Oh, we need the address too. So we have to have too much information. So dec. So if we're going to do that, how about I just say dec_mem_r. There.
Everybody make use of that repair bot.
Oh, come on. Okay, so now we need all those functions. Again, the less logic we do during the function call, the better. So search for the comma, keep that much of it. Static, void, do that, and decoder.
All right, we have a crystal
Dec.
at the stone.
Okay. Ah, come on. Okay, so we have a bunch of unused variables because we're not using those. And now we have a bunch of functions that we haven't defined yet. So these statics actually go up at the top for forward declarations. And at the top, before we do any testing, test stuff below this line. Oh boy. What do these look like? I'm going to do one, and then I'm going to do copy, paste, edit to duplicate. So inside here, what we're going to do is grab the address first. So we have word addr is equal to dec arrow adder.
Back at the stone.
Okay. And word page is equal to addr right shifted by, actually, amper 1 less than dec. There's a bunch of intermediate stuff we do here. Yeah, okay, let's start by right shifting this by dec mem page offset bits. And then we're going to mask it with 1 left shifted by dec mem as bits minus dec mem po bits. Okay, so the other way of doing this is to construct the mask, do the mask and the shift. The question is, which is faster, shift and or and then shift? I believe that there are some CPUs like ARMs which use a fused mask shift operation where which one you do first matters. I also believe that the compiler is going to be fast enough to optimize it. It will recognize this as extract a bit. In fact, on the Intel chips, I am expecting, if I disassemble this, to actually see a bit extract operation of some sort in assembly code, because that's really too useful to not define in an instruction set. So this defines a page number. We could assert that the page number is in range. 0 less than or equal to page. Assert page is less than dec mem pages.
Right. Stack of the ruins.
These asserts will go away when we get to timing critical stuff, because this is a very timing critical routine. And now we say p edge equal to.
The pants were reserved by Moose and Nazgul. You two give me a roll.
Okay, grab that.
Grab some
If
Moose.
p edge, then we say p edge we have to do some work.
The head was reserved by.
So this is specifically rise. So this is edge, high, p edge. Like that.
Got the
So
head of those
this is now,
series.
the compiler is telling us that this is always true.
Looks like Grotesca with a 95. Congrats, Grotesca.
Okay. This says unexpected identifier here, p edge. Oh, right. P edge is a very bad name for a variable. E.
We got a Druid book and a road book.
And in fact, the compiler is smart enough, I can just write that.
All those books are going to the kill bank.
So now it's got a whole bunch of things that were declared static and never done. So we're going to take memr rise and we're going to make memr fall.
And we have a hilt token for priests, mages, warlocks, and druids. Weapon token. Priest,
That changes to
mage,
low.
warlock, and druid.
And then we're going to take these two and duplicate them. And from memr,
Alright, leaving that on the body. I'm
Go to
gonna
memw.
to, copper up here.
and oops, can't just change RD. We do that. So that's got all of the memory service functions. And now we do the same thing again, but we change mem to IO. Now, with memory, we don't have all of that stuff, so the word page gets changed to word dev equal to adder amper 1 left shift by dec devices dec dev is bits -1. And I just realized that the expression was wrong for the memory stuff. We probably would have caught it when we did the testing, but now that I have realized that I'm missing a -1, we're good. So given that I have to do a -1, let's actually pound define a macro for page mask. Pound define mem adder page mask is equal to 1 left shifted by the address space bits minus actually 1U. Let's make sure we keep it unsigned. That defines the page mask. Mem page of A is now equal to A amper mem adder page mask rate shifted by page offset bits. And now this whole expression becomes mem page of adder. Now, I'm not using adder for anything else. So what I can do is I can say, change under paren adder to paren star dec like that. As long as A is parenthesized here, we're safe. And again, this guy, adder amper, becomes star dec adder. I believe that's going to be good. There we go. Okay, object is not a function or function pointer. It squeezed me. Okay, S bits, P0 bits. Gosh, I wish the compiler printed out what the macro expanded to. Oh, I forgot the closing semicolon. To her. Page undeclared. And we don't have dec IO devs. We have dec devices. We don't have IO read. We have dev. There we go. So all of the copy paste edit is done. I like to use the errors to guide that. So that was actually normal for this kind of thing, and it was slightly more reliable than trying to type them all out individually by hand. I like using the macros to isolate these operations because I used long names for the values. So this guy, these need to become macros as well. So we're going to say left, left, A, right, like that. And now this becomes dev number of the address bus. Actually, it's not even device number, it's device port. Let's talk about IO ports rather than there. Even more to the point, these are, let's make our language match the terminology of the problem domain. These are IO ports. Better. So this should now do a distribution of these 4 signals into these decoded 4 signals. Now I need to work on shadow. Now what was my rule on shadow? If shadow is set, memory reads get diverted, right? So memr if dec shadow edge high dec shadow. Actually, let's make this a guard. We're only going to do it for memory reads, not memory writes, so that you can read from the ROM and write to the RAM if you want to arrange it that way. So I am making a decision right now about the kinds of systems we are implementing. That's appropriate because we are in simulation implementation code. Mem page mask is too long. We'll call it just mem page mask. Oh, come on. How about we use some consistent indentation here? Okay. So the critical thing is each one of these functions is very small. I am going to do exhaustive testing on addresses to verify none of these asserts pop out. And that was going to happen probably in BIST. So decoder post, I need to make sure, first of all, we don't crash if we reference a device or a memory that is not there. So, 1, access to null, access via null edge does not crash. 2, delivery can deliver signal to each page of memory. Okay. And then we're going to test shadow. Shadow intercepts memory reads, ignores memory writes. And yes, I want to do all of these things during post. Post probably should just sample things. So post will verify it works for maybe first page, last page, and BIST will do the whole thing. Oh, come on. Space dash space.
Leather hound? Leather heathen hound?
There we go. We have a decoder that's full of nulls. I can now set this up
Yeah,
and
this one doesn't have
hit
as
it.
much number on it, but
We're
it is
going
a
to,
leather,
this is going to be like the
second
other
one,
one.
DE, and 3, 2, 1.
So again, the check cases here, I'm going to end up with check case functions. The idea is
We got a warrior book.
tau plus equals 1,
Your warriors need a book.
star adder equals 0, and then we're going to
Looks like that's going to be good.
check outputs. And there's going to be one specific output that we're going to be looking for, which is nothing.
And a ring token for Hunter, Rogue, Priest, and Warlock. Hunter, Rogue, Priest, and Warlock.
And we're going to do this for, oh, we need to do it for,
Grizzly, you left the raid.
let's see, oh,
You left the zone. You can't give it to me.
okay. So set the address,
Oh, that's Thunderbolt.
set memr
I
low,
wanna go to Thunderbolt.
and we're going to make sure that nothing crashed.
That's fine. No, I can't use it.
Okay,
It left the raid.
so what check outputs will do is
Thanks, Moose.
verify that all signals are, if there's anybody there, they should be a value 1, except edge,
I'm switching to my mage.
that should be 0. I'm thinking in terms of what we need to make for this to be generic. Okay, so that checks the memory read at 0. Now we're going to check the last byte. We're going to duplicate this and do it for write. Okay, now when this guy checks, it's going to check all of the pages, all of the pointers from all of the array. So can deliver, and I'm going to do this for I/O. And again, we're going to run all the address bits low and all the address bits high. So this test is not going to just say, oh, I'm only going to test port 255. I'm going to test all the address bits high to make sure that they are getting masked off. Okay, so that covers the null stuff. Next thing is it deliver read to each memory page. We're just going to do the first and last. So we're going to grab these two lines and these two blocks. But I also need to establish edges there. Mem under deck. Can I just use memRD here? I should be able to just use memRD here if I just set up the pointers. that. So I am thinking that these guys, these could be static and established but not linked up. In decoder test init. We're going to need memwrite, and we're going to need dev, like that. Okay, now we are not going to lock those in on the stuff there. I think I'm going to also set up a testing edge to be the shadow. Just call that ROM shadow. Okay. Implicit declaration of check outputs, static void check outputs of, we're going to say bit. Oh, we're always going to have a 1 there, aren't we? So anybody that isn't the edge we're worried about is going to be 1. And anybody that is the edge we're worried about is going to be 0. So p edge E is like that. Oh, I need an expected value here, bit expected. This is test support code. And I need to do this based on the global static test decoder. Got it. So what we're going to do is for int, based on that, how do I want to modify that if statement?
It looks like the stock reserve thing is locked, and we still have people who didn't get their reserves in.
ERT EQ integer. So if t is, oh, I need a if t equals e.
Since we
that.
had started. Okay, it's unlocked. Yeah, refresh the page, people.
So if t is equal to e, then I want to say expected t arrow value. Else 1. So our output signals are active low, just like our input signals are active low. And again, E could appear in any of these arrays or multiples of them. And we want to do the same thing at the top for shadow. And we also need to define those mem read write, etc. So those are unused. And then we're getting a complaint about tau because I'm not advancing tau before the edge high. How about that? That's actually calling into edge outputs here. Of course, we haven't actually hooked up any of these guys. So during post, I do want to hook up my guys here to the right thing. So I don't want to hook them up all the time, but I do want to start with this guy and say dec arrow mem underscore rd of 0 equal to mem read first. I believe I have that pointer set up. Yep. And mem read of dec mem pages -1, mem read final. Okay, so this is saying, whoops, warning suggests parentheses around minus inside. Okay, I do have parentheses around the minus, but it might be nice to have parentheses around this as well. Okay, so the recommendation for more parentheses was great, but it needed to do
Fresh
more.
perspective.
So we are now failing here, where we have t not equal to e and t not equal to 0, and we're saying our 1 is failing here. So here we need a debugger. Okay, and the first interesting frame is going to be 7, I think. So this is saying that inside check outputs of mem read first, I'm looking for looking for mem read first to be 0 and everybody else to be 1. We're getting to here, and this says the last page, and that was optimized out. Okay, so we got to turn off the optimizer to debug this.
Who was that? Oh, we walked off the cliff?
Undefined reference to
Well,
seal.
he's a rogue, he can sneak in.
What?
Oh. He needs a summon.
Did I forget to link myself with the library that provides the sealing function? Yeah, ceiling and floor.
Waterfall.
Okay, so libs. Syslibs, I need to add M for the math library. There we go. So we're still getting a segmentation fault somewhere. Sunny Beach, Sunny Beach. Run. Where? So we're calling format. Haha, 8228 init. We're calling format, and somebody is unhappy. Well, looky there. Not enough parameters given that string, so I need to say common name. Not sure how I missed that.
Something happened to the master loop. Yeah, I believe you did on that pack there, so.
Okay, so
Send all those coins, Stevie.
check condition failed, expected value 1, observed value 0. So somebody was low that should have been high. We're back to that, and this time we have our debugger available. So frame 7, and it's putting our source over on the left. Come on, GDB. I do not know how GDB decides which window, which pane to put it in. But we are here at line 305. We are now here. So for some reason, we are getting that one set. Let's start printing out exactly what's going on here. Three octal digits for the page number. V equals, actually, let's print the page, T-arrow name, T-arrow value. At the top, I'm going to say expect only that, and E-arrow name and expected. And you know, I can start off the top with assert. So now the rest of these, I no longer need to say if t equals E. I just say if t not equal to E. So first thing we're going to do is we're going to check that that edge is what is expected, and then we're going to go through the rest of them, and any that aren't that guy, we're going to check that it's 1.
Who can DE for me?
There. Okay, now we're back to segmentation fault, having printed nothing. Ah, right. Check outputs. If I pass a null pointer in, it needs to not crash. Okay, so here we're getting the prints. I keep forgetting that I don't need a do line on the end of the stubs. It takes care of that for me. Okay, so we expect no signals to be active a bunch of times. That's boring now. So expect only memread first to be there. We get read first and final is 0 because we did not initialize our signals to high. There we go.
We had 4 people on the item.
Bug in the test. And we printed a whole bunch of things.
Coumadin, diagnosis, no life, and calorie.
And that's all correct. So now I can put backslashes in front of these guys. Oh, we haven't actually executed these guys
We
yet.
have a warrior type cloak,
Okay,
tank cloak.
so I'm going to keep that stub going, and the other stubs will tell us when we get those parts of the test working.
Going to DE in 3, 2, 1.
So we set up memread.
Let's stay
At the end of it, I am going to
triple strike.
I'm going to leave that set. Actually, let's set up all of our test signals.
Okay. Going to DE in 3,
Like that.
2, 1.
And this is deck dev pages. Of course, that is an error.
Shawl token, Hunter Mages.
That's deck IO ports. Okay, so now we are getting into these stubs. And the only thing left to print is at the top. I'm going to go ahead and comment that out now. Now we just need to can deliver read. Next is can deliver write. Bada boom. And these are no longer going to be, they're going to be duplicated instead of mem pages. Oops. We are going to say
There is a pat on the road.
IO port. Now we do the same thing with shadow. Okay. Same set of tests, but this time with the shadow involved, it's going to change what actually happens. Called ROM shadow, not shadow. Okay, test condition failed here. Let's switch up to frame 6. So we are failing in the expected guy here. Which is checking the outputs that ROM shadow, it goes to 0 when memr goes active. So the shadow is not being set up, or not being honored. So memr rise and memr fall need to handle shadow, and they are supposedly handling shadow. Ah, there we go. Nope. Yep, fall is edge high, it needs to be edge low. That's it. So now we have a whole bunch of prints about expecting only that I turned back on temporarily. And we're good. So we have now verified that our decoder can decode first and last of each address space and that shadow does the right thing. Let's repeat the same thing for BIST, but I'm going to do it exhaustively. So we are going to need many, many, many more pages. Do I need to, oh, hold on. Do I need to do it exhaustively? You know what? I don't think there's any meaningful built-in self-test that is beyond that. We'll just repeat the post for now. And later on, we may extend it in BIST and we may compress it in post. But this is fast enough and good enough. Is there anything about this we want to benchmark? I don't think any of this code takes any significant time to run. So I don't believe there's actually any importance to benchmarking the decoder here. So the upshot is we end up, oh, I do need to start wiping out asserts yeah, so we need to assert, get rid of the assert page equals, flush, page range. That would have failed if it was going to fail. And I'm going to change this to what? I'm not going to change it. So all of these functions are time critical. So they check shadow and dispatch if their memory reads. Fetch the address, extract the page, grab the pointer, and pass along if appropriate. I suppose I could benchmark how long it takes to run this entire test, and we could talk about the number of decodes based on tau. Yeah, we could do that. So we now need a static void bench decoder. Just going to do all of this stuff. Decoder init is already called. I'm going to ignore, well, I don't want to use the nulls. If we're going to do the nulls, I need to, do I want to benchmark initialization? No, because initialization by definition is going to be doing asserts. If we want to test the null stuff, we would have to null things out. What I'm going to do is I'm going to leave things hooked up here in decoder bench. Need to make sure to turn off ROM shadowing. Actually, let's not benchmark ROM shadowing. That's not going to be our critical path. ROM shadowing will actually be a little bit faster, but it's not something we're going to be running in the bulk of it where we're running with RAMs. So what I'm going to do is this. So we're going to benchmark how long it takes to access each page of memory and each I/O device in order. Remove the check outputs. And we no longer need these guys.
Hunter mage token, hunter mage token.
We do need them here. Hold on. Oh. I flushed all the check output stuff, forgetting that we had the declaration of the function at the bottom. So bench decoder is the function I want to call for the benchmark. And tau t0 is equal to tau, and static tau bench d tau come on. So we will have incremented tau by 1 for each edge we sent. So E undefined because we're passing in a 0. So this says I'm taking 19 nanoseconds per thing. And the optimizer's off. So that would have been a clue when I looked at the rest of this and realized all the other numbers were a bit high as well.
Well, I think somebody clicked on the voodoo pile because I was seeing the snake was sheep. I couldn't figure out why there was a sheep in.
Okay, so 6.3 nanoseconds for us to receive the notification that the signal changed and to go find out who we should send it to, which involves looking at shadow and then looking at the array pointer and diving through that to get the item, and then looking at the edge and delivering to edge. So 6.3 nanoseconds to decode. I am a little bit disappointed in that number. Surely I have made a mistake somewhere. So let us go cast our eyes over those functions. This is dec underscore whatever, rise and fall.
I'm just saying it right now. There is no soft reserve on the Tiger.
Okay, so let's see.
Yeah, I'm just trying to, get y'all psyched up here.
We're going to cache that in AP edge. E equals that. We're going to say if E, we're going to go to there. And then I'm going to go on to the next one. This shouldn't make any difference if I understand what the optimizer is doing. So 6.3, 6.6, 6.5, those are all within, 6.1. So the optimizer is actually make it so I don't have to do this. This shouldn't be any slower or faster, but it might be. Shadow should be ignored for these guys. Right. Yeah, these aren't making any difference in the runtime, but it does make it clear exactly what the operations are. So let's use it.
There was no software server on the mouse. Ritualistic leg guard. Cloth. A lot of healing.
IO page is
Going to DE in 3,
dev port.
2, 1. Anybody need some sacrificial gauntlets? These are very, very nice for new warriors.
Okay, now IO.
Going to Grotesca.
Do IOR now.
And we have a token here for Warrior Road Shaman. Warrior Road Shaman.
Okay, so we're still sitting at about 6 nanoseconds for the entire thing, but at least now we can look at this and we can say, okay, we know exactly the sequence of operations that is going to happen in assembly code.
Got a blood side? So anybody need a blood side?
Let's make absolutely sure that the optimizer is on OFAST. Yes, it is.
Herbalist so that you can herb in here and get blood funds. All right.
Okay. Well, it's better than having every single chip be notified every single time the DBN signal wiggles. But I can't help but thinking that there's something else that's happening during that particular benchmark.
Grizzly Bear, you have to go back to the little tiger cubby and loot it. It's in that hoodoo pile in the middle of the tiger cubby.
Yeah. I don't see anything else that could be happening. The other thing I could do would be to repeat this a few times. Try to amortize out any benchmarking overhead beyond what the benchmarking does. And that makes no difference, of course, because the benchmarking just runs this function call in a loop. That's what I want it to look like. Now let's try the keyboard macro again. Edge underscore low of that becomes dec trigger of that. And we go up to the equal sign, and we clip from there to the end, go back to the end over there, and we're going to clip like that and like that.
You might want to wait and see if we get any from the hut.
Okay. No change in performance because a good compiler will just inline dec trigger, but that really makes it more clear. We're triggering memread for 0, memread for F. And I'm going to furthermore say 0 to comma 0x FFFF and 0. Oh, wait a minute. Octal. We need 16 bits of octal. So this is 0, 7, 3, 6, 12, 15, 16. So there is our maximum address. I'm going to leave the 0 as just a 0, rather than having a whole bunch of zeros. Now, that's actually what I really want is a word, not 0. So all the bits that fit in a word. There. So can I do this without casting it? Suppose I can. Nope. I have to remember to put the closing parenthesis and the closing semicolon in place. Yep, there we go. Now, I just noticed that we are not testing. IOR, IOW. So, yeah, there's dec bench trigger. I'm going to do the same thing with dec test trigger. These are going to be, oh, come on. Dec test trigger, which is going to be up here. Needs to do a check outputs. Call this PHO. So we need the edge that we're wiggling and the edge that we're expecting to wiggle. I have to type this without making any errors in the search string. It's frustrating. Search check, because I insist on using the incremental search. My own fault. So the first edge I want in there is this guy. And then we want the address, which is this guy. And then we want this address, this edge, and nothing else. And I managed to do that badly. So I'm going to need to delete some things by hand, but I'm not retyping that macro. Okay, those are the tests for the null pointers. Now I'm going to type the macro again because I have to use this for the rest of them. This is search for check underscore outputs. And we delete that. We make it dec test trigger. And this is going to be this guy, followed by the address, followed by that guy, then we wipe out the rest of the block and the blank line before it, and we're there. Okay, tests are back to running again, and we're still getting about 6 nanoseconds. That's correct. And now our big test case up here is fitting on one screen. That's yay. Now, are we testing to make sure that dec shadow is doing nothing in the test cases? Yes, we are. So shadow, if we have a shadow and it's not equal to E, then we assert that it's 1. So we are testing all of those cases. Oh, right, expect braces because this may group differently from what was expected. Yay, broken operator precedence in the C programming language. Suggest explicit braces to avoid ambiguous else. probably because a CertEQ integer has that if-else in it. Yeah, okay. So the compiler doesn't like my old trick that I used in my asserts.
All right, you know, roll from diagnosis, no life, and calorie for the idle.
So yeah, this trick is,
Going to no life.
the other way I could do this is put in a do semicolon while 0.
This is a caster DPS string. Going to moose in 3, 2, 1. Have a healing cloak.
So now I can get rid of these
Very
braces
nice healing cloak.
without an ambiguous else.
Pursuit set 2. Going to perk out.
Now, do while 0 is convenient because literally any token here other than a semicolon or beginning of a comment is going to
Hunter
cause
Road
problems.
Priest.
Okay, we good now. So I didn't yet convert these guys, which need conversion, and the easy way to do that is by grabbing the one that already has it, because we haven't diverged post from BIST yet.
Okay, so nobody.
So I believe that this is the decoder as it's going to stand. We're going to have to deal with the about 6 nanosecond cost to do the decode. Which I'm still not happy about. I'm going to disassemble some of this stuff. So what does dec memr rise look like? So let's see, NPR 64, move test JE down to plus 32, move jump, nopple. Okay, so it's kind of a weird order, but yeah, so obviously we are getting R8 from shadow, and we are comparing for not equal to 0. Right, test R8, R8. What? Sometimes modern x86 assembly code makes me scratch my head. So test %R8, %R8. And then JE. As a person reading that code, I'm thinking if R8 is equal to R8, we're going to jump. It should be, well, if they're not equal to, then we're moving R8 into RDI and jumping to edge high. So this is that dispatched edge high all the way down here. So it has optimized this out to say if E is a pointer, we just go right down here. So that was well done. Now we get down to 32. I don't think we ever execute that instruction. Get down to 32, and we pick up offset 8 from Rex and mov ZWL. Shift right. Okay, so this gets something into EAX, specifically AX. Now we right shift by 10. That gets the offset. And then we AND by the mask. So for the x86, it does the shift and then the mask, even though I wrote mask and then shift. So good on the optimizer. And we grab the pointer. And again, test R8, R8. And if it's non-zero, which has got to be what that is, then we branch back to plus 16 and do this. So this nopple is not an instruction we execute because I don't believe the x86 has branch trailers.
All right, tokens get left on the body.
So I don't see any way this could be any more compressed. I mean, it's literally just doing the operations that I need done. So the other possibility is that I am leaving a whole bunch of things connected up to my signals that I'm wiggling. Okay, so for instance, what is out there on Memar? I think as part of decoder test init, I'm going to add some assertions. So a pre-test and pre-bench invariance. Memar W have one entry on each list. Okay, didn't fail, which means we have only one entry on each list coming out of the initialization code. And we do call test init at the top of bench. We have no subscribers on any of our output edges. Let's assert that as well. Okay, so we have no surprise subscribers, at least coming out of here. Nope. I don't see any place where any surprises could be lurking now. I never thought I would complain about a piece of code like that taking 6 nanoseconds to run, but when you're running CPUs at 5 gigahertz, yeah, that's 30 CPU cycles. Maybe it's just because I'm doing a number of round trips to memory to do this, where we've got these cascaded. I've got dec pointing to dev_rd, which is an array, so I have to do an array address calculation here, and this is a pointer which points to somebody else, and yeah, maybe there's just too much pointer chasing. I don't see any way to eliminate it at this point, not from this level. I think we have done as much pointer tail chasing elimination as we can do on this. So I am going to call this a working decoder. I will do a once over to adjust and increment comments to update the README. And other than that, I think we are done. So at this point, I'm going to sign off. So keep your code fast and keep your code safe. Talk to you next time.